G'day guys, today we're going to exploit default package and binary gopher for 32-bit x86 that is in Kali and is probably in related Debian distros as well. Gopher is unprivileged, so not that useful to an attacker, but it is a good educational activity and is on a default version of the package. One of the reasons that this is interesting is because there are actually still some packages and binaries compiled without all the mitigations, so we can actually use some of the exploit techniques that we've been doing in previous videos. So let's install our program, which is gopher for 32-bit. Takes a few seconds to install. It'll almost be there. There we are. Let's install the source code for gopher so that we can actually see the bug itself. The bug is an environment variable based bug again. And we can see here we have home containing a pointer to the home environment variable, and here a string copy into a fixed size buffer classic stack overflow. Let's see anywhere else. And here we have more code related to this style of classic stack overflow, incorrect length validation of path or incorrect memory allocation for what it's being copied into. So that's the bug. So let's see if we can trigger this bug, and we'll just create a big string and we get a seek fault. We don't get a stack overflow detected aborted error, which is probably is a good sign for us and indicative that it might not be using stack canaries. So let's go into GDB, and we can see that we control the instruction pointer. It is all A's. So that's good. It's not using stack cookies. We control the instruction pointer. Let's find out our exact length that we need. And this will create a cyclic pattern to enable us to find how big the buffer is before we overwrite the return address. So let's have a look at that. A long cyclic string. Let's load it in GDB. Here we go. So now let's use a related tool. Our query. And we have the size of our buffer that we need before we overwrite the return address. So let's write our Python code. We use the OS and struct imports. Our buffer equals is padded 268 characters, and then comes our return address, and we want to create our home environment variable. Let's create a prog name as well. There we go. It doesn't use stack cookies, it is a non-executable stack and heap, and we'll assume for now that ASLR is not turned on, but we will turn it on later. So let's actually turn off ASLR. And we're going to do a chained return to libc. All we're going to do for our return to libc is return into system, execute the shell, and then do a clean exit after our shell exits. So let's keep our buffer, our home environment variable large. Okay. So let's have a look. Let's load the GDB Peter plugin and run our program, and we received a seg fault. Okay, so let's find our system call. Let's also do exit. So we have our exit call there, not using ASLR, so this is static, and for our libc version. Let's also find the address of the bin sh string, which will be our argument to our system library call. We have we also just want to keep a return value, for our exit call. Okay, so we want to chain two things together, a system and an exit. We're going to call system first. This is our return address. Then we need the return address after our system library call exits, and we'll leave this as a placeholder for now, but this is how we chain into the next part. So the next part, we have our exit, we have our return address from after exit, and then we have our argument to exit. And I've just forgotten something as well. After our libc call, of course, we need an argument to libc. To our system call, we need the address of our bin sh string. Format is quite simple. The address of the call, the return address after the call exits, and then the arguments to that call. So how do we chain the first part to the second part? We're going to use a few options here. We'll use ROP gadget, or we can use ROP search. And we're going to lift ESP and it's going to move this stack pointer past the argument and then return into this libc exit. And there's our exploit. Okay, so let's run our exploit. Now we have a shell. Great. And we exit, and it exits cleanly. with -1 truncated by the shell. Let's turn on ASLR again, and we notice our exploit no longer works. So let's do brute force of ASLR. And then we have a shell. Let's do that one more time to see. Break out of that. And we have a shell. Brute forcing ASLR. So one more time. And in 69 attempts, we brute forced ASLR. So this was a default compiled unprivileged program, gopher, and we gained code execution via a chained return to libc exploit. So my Patreon page is at patreon.com/infosect, or otherwise go to YouTube and check out the other videos that we have. Thanks for watching, and I'll see you next time.